to welcome Shafiq Joki. Shafiq is a research director at Salesforce AI Research, and he's also a professor at the Nanyang Technological Institute of University in Singapore. So Shafiq has done a lot of work in various areas in NLP and machine learning. Actually, first got to know his work on this course for NLP, which is kind of quite early, 10 years ago, and we still haven't solved that problem, right?
Yeah.
So now today he's going to talk to us about large language models, which we all love, right? And I think I'm very excited about this because I think coming from Salesforce, he can provide a different kind of perspective that we've heard before. Okay. All right. So with that, let's welcome Shafiq.
Thanks, Kevin, for the nice introduction. So this talk is going to be about unleashing the potential of LLMs through task and data engineering. But I'll also talk very briefly about our in-house LLM, which is XGen. And feel free to ask me questions at any point of time. Okay, it will be good if it is interactive. Okay. So this is going to be the outline of this talk, how the rest of the talk will pan out. So let's start with a background from where I'm coming when I mean the role of model, data, and tasks in LLMs, and give more of a historical background to that. And then, as I said, I'll briefly talk about our in-house LLM, which is XGen. In particular, we only released the first generation of that. The latter two generation, XGen 2 and XGen 3, we did not release it. But I'm going to just talk about the first one. And the significant part of my talk will be about task engineering with LLMs. In particular, knowledge-enhanced reasoning, how to unleash low-resource translation and cross-lingual capabilities from LLMs, especially for low-resource languages, and data distillation from larger models or API-based models to smaller models for code generation. Okay. So just a bit of background. If you're doing NLP before 2014, just like me, I think a significant part of your effort would go into feature engineering, where you'd be interested in extracting linguistic and other features that are useful for your tasks. I mean, this is good, but the only problem is that it requires language, domain, and task expertise, which can be quite expensive. Now, over the last decade or so, we seem to have moved from feature engineering to model engineering, where the goal was to design novel neural architectures with better inductive biases for the problems at hand. So we now have models for sequences, neural models for sequences, for tree structures, for graph structures, for two-dimensional images, and also for three-dimensional video. And in most of the cases, you can train these models end-to-end. So when it comes to the LLMs, it seems like we have converged to a kind of point that transformer decoder has become the standard for LLMs for unknown reasons. We don't know whether BART scaling BART can solve the same problem, but at least for now, what we have been seeing is that transformer decoder has sort of become the standard architecture for LLMs. And in particular, it uses causal self-attention for representation learning, and it uses causal language model as the pre-training objective, where you train the model to predict the next token given the prompt or history. So other neural architectures that have been tried is encoder-based models like BART, and also encoder-decoder models like T5. So now, on the data side, we are now witnessing a bit of renewed interest in data engineering, and especially if you are following Andrew Ng, who has been really kind of advocating for data engineering. And some of the examples when it comes to data engineering for LLMs, this involve applying the most effective preprocessing techniques, like what is the best tokenization that you should do. This is important because in most of the cases, you train these models in a multilingual setup. So what is the best tokenization that you should consider? Then how to determine the right mixture of data sources. And this is very important when you are training or pre-training an LLM. Then how to deal with inconsistencies in the data labels when you are doing supervised fine-tuning or let's say DPO-based preference learning. How to identify biases and toxic content, and also making sure that you're getting rid of the contamination. That means your training data does not include your evaluation data. And then how to use effective data augmentation and distillation techniques. Yeah. And over the last couple of years, we are witnessing a rise of task engineering, where the goal is to have a single model that can solve many tasks, even unseen tasks. And so we are now witnessing a lot of prompt engineering, and you usually train these models in many tasks with the hope that they will generalize to unseen tasks. So you can fine-tune these models on hard prompts, or you can even fine-tune these models to learn task-specific soft tokens, which are also called prompt tuning. Now, when it comes to the task engineering, the fundamental questions are what tasks to consider. And within that question, how to enable use of, let's say, external tools via API like LLM as agents. We are witnessing a lot of effort on that, enabling LLMs to use or to call APIs. Then a more fundamental question is, what is the right objective or reward when you are using reinforcement learning? Traditionally, we have been optimizing accuracy. But what about the protected attributes like age, color, gender, race, religion, and so on? What about the privacy and security issues of the model? So we have now alignment research, where the goal is to align LLMs to human instructions and values. And we measure the LLMs on helpfulness and harmlessness measures. Okay. So here's sort of with that context, this is sort of the standard LLM life cycle. So start with a pre-training. And usually you pre-train your model at least 1 trillion or 1 trillion, I mean, more than 5. I mean, the recent Llama 3 has been trained on 15 trillion tokens. So initial scaling law, I think, underestimated the role of tokens. But now, as you see, the recent models, they have been trained more and more tokens. So the role of data was initially underestimated in the scaling law. But now I think people are realizing that data is probably more important than model scale. And then this data typically contain text and code, unless you are doing multimodal language models. And it has been shown that, in general, the large models, in terms of the parameters, they are better in context learning capabilities. So that's why GPT-3 was 175 billion, Llama 2, and also Llama 3, they have 70B model. So now once you have the pre-trained model, then you go into fine-tuning, where the goal is to align to many diverse task instructions and labels, and also to make the model honest and harmless. And in general, the traditional way is to do it supervised fine-tuning, and optionally to use DPO or reinforcement learning with AI feedback or human feedback. But that is optional. If you have enough data, SFT data, you can possibly bypass the DPO or preference learning. Now, the challenge here is how to get diverse task instructions and input-output instances. And this is more important to have this, especially the SFT data, to be high quality. And then we try to evaluate these models in at least 3 different setups. One is where your instances are held out. That means you have seen the task, but the task instances are held out. So this is the standard supervised learning setup. Then you want to also evaluate this on a setup where the tasks are held out. That means you have seen similar tasks, but not exactly that task. And finally, on the tasks that are completely unseen. So that is probably most important when it comes to the instruction tuning of these models. Okay. So when it comes to LLMs and AI libraries, Salesforce has always been a key player since 2017. It invested a lot in LLMs. So some of the initial effort like DECA NLP, which is modern day instruction tuning, was actually proposed by Salesforce. And I have been part of also many of these large language models like Code T5, then Bleep, like Albep was the first version of Belief, and most recently we have XGen model. So I'll first talk about very briefly about XGen, and then I'll go into the main part of the talk. So for XGen, as I said, this is the first generation that came just before Llama 2 and after Llama 1. So our goal was to outperform Llama 1. Okay? So we trained a 7B parameter model. And it was, at that time, most of the models were supporting 2K sequence length. And we managed to do this for 8K sequence length. And we trained this for 1.5 trillion token. But the learning experience was that at that time, we learned that tokens are probably more important than the parameters. So that is one thing that we learned at that time. And another thing we learned is that you can train this model in like stages. So you can first pre-train this model on 2K sequences, and then it's easy to retrofit this model when you go to 4K and 8K. So that was another thing that we learned when you train these models, that retrofitting these models is relatively easy. So you can have less compute to retrofit this to larger sequence lengths. And that learning, actually, we have been using it in the subsequent generations like XGen 2 and XGen 3 that we have now in many of our production use cases. And another goal we had when we are training XGen 1 is to have a model that can perform both in text and code domains, because our use cases at Salesforce encompass both coding applications as well as textual applications. So as I said, mixing the data or the data sources is really important when it comes to the performance of LLMs. So we train these models in 2 stages. First, the first stage was mostly text heavy. And then in the second stage, it was like 50-50. And we just used OpenAI's BP tokenizer and some code-related special tokens for our pre-training data. And for the library and hardware, we use JAX format, in-house optimized JAX format. It supports both data and model parallelism, and it was optimized for TPU v4. Now we are using v5. And it was done with a pre-32 precision, but it was for the matmul, we are using 16. So for the training recipe, we mostly followed Llama 7B because that was our goal, to beat actually Llama 7B at the time. The only exception is that we increased the token budget to 1.5 trillion rather than 1 trillion. And we did a stage-wise training, as I said. So most of the training compute was dedicated to 2K trillion, and then we retrofitted that model to 4K and 8K. And also we increased the lookup size to 51K tokens. So that's all about XGen, because I mean, I did not show the results because those are now obsolete, I guess. So any question at this point before I move into the main part of this talk?
You said data engineering is important. How important is the tokenization scheme and the number of vocab? How do you guys?
Yeah, so I mean, we did not, because for the large LLM training, it's really very expensive to do a lot of applications on that. But we saw that if you increase the token, I mean the lookup size, and if you support many different domains and languages, you need to be proportional to that. So as many hookups or as many items you have in a hookup item, that helps if you have diverse domains and languages. But we don't have any report on that on the hookup side of the tokenization. And for our ablations, we have been mostly using a smaller model. as I said, like we are not like Meta, who can have like a huge amount of resources. So our ablations are mostly on 3B and 1B models, and then we try to see the same progress in the larger model like 7B, and the largest that we trained so far is 33B. But yeah, we are also doing mixture of expert of those models. Any final question or any other question? Okay, so now let's move on to more on the research side of LLMs, or more like published work. So one key challenge in LLMs, as you all know, is factual correctness. And it seems like it's an innate shortcoming of generative models. Or it may happen that the model contain outdated knowledge, or even though it might have the knowledge, but it just cannot recall the knowledge properly. So it ends up making up facts. So it has serious consequences, especially if you're building an application for domains like medical or financial domains. So it has ethical concerns and safety hazards. Now, it turns out that chain of thought, which I think by now everyone knows, it improves the LLM's abilities in complex reasoning tasks. So I'll not explain how it works. It's just like the main idea is that you, rather than letting the model generate the answer directly, you first generate the reasoning chain so that the LLM get more context to generate the final answer. And so it helps the LLM to generate the final answer correctly. But what if the reasoning chains are factually incorrect? So here's an example. What year was the Argentine actor who directed LTO at Dispatch Bond? So if you use even the most up-to-date LLM like GPT 3.5 or GPT 4, it may find these rationales incorrect. For example, the first rationale is incorrect in this case, and then the error propagates to the second rationale. So the question here is, can we revise a bad reasoning chain to be more factually correct so that the model gets better context to generate the final answer? So with the hope that it will in turn generate the answer more accurately. So as humans, how do we approach a complex question? So at least this is at least I follow is that if the answer is certain to me, I'll probably just generate it or answer it from my internal knowledge. And if I'm uncertain, then I'll probably look for external evidences. Right? So I'll retrieve external evidences from additional sources like Google if I'm not certain. Now, the question is, how do we know that the LLM is uncertain? Because if you just ask the LLM, it will always say that it's very confident in its own generation. It turns out that the self-consistency could be a good approximation, which can be also explained by the minimum base risk theorem. So the way that self-consistency works is that instead of sampling only one reasoning path, you sample multiple reasoning paths, and you take the majority vote. So if you sample, let's say, 10 reasoning paths, and 7 of them are giving you the same answer, so you take that as the confidence. So we can use self-consistency as an approximation to measure uncertainty in LLM's reasoning. So then in step 2, what we do is, once we are sure that for this particular reasoning, the language model is uncertain, we look up for external evidences. And to do that, we convert the reasoning that was initially generated by the LLM into a query and retrieve external evidence and then synthesize that to make the final rationale based on which we put again as prompt to the language model and generate the final answer. Okay. So this is the work we call verify and edit. So basically, we generate verifying questions, get external evidences from external sources, synthesize the reasoning chain again based on the external evidences, and generate the final answer. So this is how it works. So given a question like this, of all the teams John played for, which team was known as the black and whites? So if you just ask the LLM to answer the question, the answer is wrong, which is Newcastle United is wrong. And then if you just ask chain of thought, you do chain of thought without any external evidence, again, the language model, the reasoning is wrong. So the final answer is also wrong. And we find that for this particular case, the language model is also uncertain. So that means the self-consistency score is below 50% for this case. So invoke our method. That means we generate for each of the reasoning questions here or reasoning sentences here, we generate a verifying question and retrieve relevant information from external sources. And then we synthesize that to generate the final reasoning chain and put it as context to the language model to generate the final answer. Okay, so that was the approach that we presented at ACL last year, verify and edit. And it showed improved results on hotspot QA. And also we did human evaluation on the reasoning chain, like how factual, how much improvement we are getting on the factuality of the reasoning chain. And it shows improvement both on like end task as well as on the human evaluation of the reasoning chains. So I'll not go into the details of that because this is again a bit old work, but I'll be happy to answer questions for that. Okay, so let me talk about the more recent work along that line, or down that line. So we found when we are doing the error analysis, we found one key limitation of verify and edit, and also one kind of fundamental limitation. So the fundamental limitation is that it was only supporting one kind of knowledge source, which is either Wikipedia or Google, kind of unstructured text. So can we support multiple different kinds of knowledge sources? Maybe tabular data, or maybe other kinds of like knowledge graphs. Okay, so how can we support different kinds of knowledge sources when we are retrieving these evidences? So that is one limitation of the verify and edit, because it is only restricted to kind of unstructured text. The second limitation we found in our error analysis is that since we are kind of doing parallel search for each of these rationales, if we have corrected the first rationale, the second rationale was still based on the previous one. So we need a sequential approach. That means if we correct the first one, that correction should be taken into account when you are generating the second rationale, correcting the second rationale. So here is an example of that. Since we are doing kind of parallel search or parallel retrieval for each of these rationales, the fact that the first one was wrong, the second one, even though factually it is correct, but the error of that was actually propagated to the second one. So that means when we are generating or correcting these rationales, we need to have a sequential approach, one step at a time. Okay? So that was another change that we wanted to make. So now, how to support heterogeneous sources? In our case, we want to support both unstructured and structured sources. More specifically, for the structured ones, we want to support Wikidata, like the knowledge graph, and also tables, because a huge amount of knowledge are in this form. So then the question is how to query these different sources effectively and how to aggregate this information. So we propose a robust query generator and also a dynamic knowledge adaptation to aggregate knowledge from different sources. So the change from verify and edit and the next work, which is we call chain of knowledge, is basically supporting multiple knowledge sources and aggregating information from multiple knowledge sources. So in a step on, we ask LLM to decide more of a domain classification, which knowledge source I should look for this given a question. So in addition to the chain of thought reasoning, the LLM will also do this kind of domain classification or knowledge source classification. For example, in this particular case, let's say given this question, the question that I was referring to, the Argentine actor who directed a particular film, the identified domains are actually factual domain or general fact domain, which is, for that we support Wikidata and Wikipedia. So Wikidata is knowledge graph and Wikipedia is unstructured text.
Question?
Yeah.
So is this different from the standard, tool use script?
It's actually an example of that.
Okay.
Exactly. So, I mean, it was done early, I think, late 2023. So we did not generalize it to many other tools, but it's exactly that the tool uses in this case, like different knowledge sources. Yeah. But we did not do any special fine tuning like tool former.
Right. Okay. So you did few shots, right?
Yeah.
It's
pretty fun.
That was what tool former started with as kind of a proposal distribution.
Yeah. But I mean, they also did a fine tuning, I think, on the API, like the calculator use and all this. Any other question on this? So then, once we have that, let's say we identified, we need to look for these sources, how to generate the relevant query for that particular source. So if it is, let's say, knowledge graph, we need to generate a query in a Sparkwell, right? If it is in tabular data, we need to generate a query in SQL. So we need to generate a query for each of the reasoning step and execute it on that knowledge source, get the evidence, and combine this, because we will be, for the same question, we might invoke multiple knowledge sources. And then once we have a correct, let's say, external evidence, we'll correct the rationale and go to the next rationale and start to get evidence for that and correct it. Okay. And finally, we consolidate. So the whole thing looks something like this. So given a question like what year was the Argentine actor who directed El Tío Desperate Bond? So we'll first do chain of thought, but one additional thing is that we'll now classify we'll now identify which knowledge sources to look for. And then we'll go to each of the rationales and try to correct it by getting external evidences from these tools or from these external tools. Okay. And as we correct one, we ask the LLM to correct the next one, or to generate and correct the next one. So that is another fundamental difference from verify and edit, that we don't do this at once or in parallel. Okay. And for query generator, we support at least different kinds of queries. Even for natural language, if you are using like more traditional sources like Wikipedia, you can rely on ChatGPT to give you the query or to give you the question. But when it comes to a special domain like medical domain, we found that even ChatGPT is not reliable. So we had to fine tune a Llama model with LoRa fine tuning for that. Then for structured languages like Sparkwell and SQL, SQL turns out to be better, at least good with ChatGPT, but not a Sparkwell. So again, for a Sparkwell, we had to fine tune a Llama model for that. So this is the work that we'll be presenting at ICLR in a couple of weeks. So if you are at ICLR, you can also listen to the talk. So now let's see the results. So we kind of did evaluation on many different domains. On the general factual domain, we had fever, which does not have many of multi-hop reasoning. Then hotpot QA, which has like 2-hop reasoning, and then Feta QA, which is tabular question answering task. Then on medical, physics, and biology. Okay. And you see that the chain of knowledge actually could outperform the existing methods by significantly in most of these measures. And we also compared with React and the 2 variations of React that they proposed that combine with chain of thought with self-consistency. And it was showing better results for that. And then we also did some analysis on how often we are using kind of multiple domains for answering a single question. And we found that, so on the right-hand side, you could see if to answer a question in medical domain, sometimes the model was speaking of biology because it was relevant to that. But in most of the cases, it was still just one single domain significantly. Like in most of the cases, just on the single domain. But we supported multiple knowledge sources for each domain. I said for factual knowledge, we had at least three different sources. As you can see here, for factual, we had Wikidata, which is knowledge graph. Then we had Wikipedia and also tabular wiki tables. And we showed that actually, if you expose the model to many different sources, we can actually improve. So that is what the table at the bottom is showing for the medical domain. And we did the same evaluation on the factuality. Did we actually improve the reasoning chain factuality? And it also shows both in automatic measures as well as human evaluation. Okay, so I think I'll take a pause here, and before I go to the next segment, probably I'll ask questions. Any question before? Yeah.
So the syntax and the structured data you learn by fine tuning.
Yes, we also gave sort of the schema as a form. Yeah, I mean, in this case, it was just Wikidata. Wikidata. I mean, we did not have very complex tables.
So I think the most interesting thing to me about the paper is the idea that first you generate a rationale that may be wrong, or a step in the chain of thought that might be wrong. I think of rationales as being like post hoc, whereas this is pre hoc, I think.
Yeah, so I think in this case, the rationale are like pre hoc.
Yeah, okay. So you generate some statement in the chain of thought, and then you correct it.
Yeah.
And so it's a neat idea because it tells you what to ask the knowledge source.
Yeah.
But how's the recall? In other words, what if there's knowledge that you didn't think of to ask about, and it still has some bearing?
Yeah, so I think as I said, like we only invoke this method when the self-consistency is below 50%.
Right.
And also most of these questions in hotspot QA and others, they are like factual questions. So your question is like whether we found the knowledge there or like
no, my question is you have to come up with something in order to go query the source.
Yeah.
What if you don't come up with the right thing? So what if there's something really relevant, like you thought Bambi was a person, but actually Bambi is a deer, and you didn't ask about, you didn't say, oh, Bambi is a person. Let's go look up Bambi's species.
Yeah, so I mean, in this case, we are not taking an automate. I mean, our decision for that is only based on, let's say, self-consistent in this case. But I mean,
that's a decision about whether to correct.
Yeah.
So I'm saying that,
or even whether to search, because that requires extra compute, right? So whether to search for external evidence is only coming from the self-consistency. We don't have a kind of.
Yes, my question is about which searches to do. So the searches you're doing are much narrower than a RAG search. A RAG search is like, let's just pull in anything about Bambi, rather than ask the specific question, what is Bambi's species?
Yeah, but in our verify and edit, and also this one for the honest, I mean, for the hotspot QA questions, we are actually searching Wikipedia, Google, and other sources, like I think Wikipedia and Google. So yeah, it's kind of restricted to Wikipedia and Google also. Did that answer the question? Or, I don't know.
Well, I'm really asking an error analysis question. That when you get it wrong, how often did you get it wrong because you didn't call the right, you didn't make the right call. You just didn't know what tool call to make because the tool call you needed wasn't a correction of anything that you already asked.
So I think this might answer some of your questions, like this figure. I mean, this is for verify and edit, where I'm showing different knowledge sources. So dataset is more like our kind of oracle. So if you see the gap there on the data set, like for Harvard QA, you have this knowledge. So you can have this kind of upper bound. If you are accurate on your retrieval, you can actually get a big jump. I mean, if you get a big jump, if you are, let's say, if you are looking for your knowledge on the data set, while you have kind of the ground truth there, or the oracle.
Right, so I guess my question is, would you go up to 80% if you had a human oracle or some other kind of oracle decide what queries to make? So, I mean, that's hard to do, like, I don't.
Yeah,
I don't know
I
how to
mean, yeah. I think it's also limited by the LLM's reasoning capability, but yeah, you could expect that. I think the main bottleneck here is probably the retrieval one. That is what we saw.
Yeah, okay, thanks, and sorry for the question.
Oh, it's okay. Sorry. Okay, so now let's move on to more like multilingual or multiple languages. And then we'll move to code. But first, multilingual. So what about other languages? So far we have been seeing this kind of capability in English. But what about other languages, especially low resource languages? And this is important because LLMs, they are usually trained on dominant English language disproportionately. And even for XGen that we showed, we only included the Wikipedia multilingual corpus. We did not include huge multilingual data because it kind of affects the performance. So I think that is true even for the Llama 1 and Llama 2 models. So when it comes to the low resource languages, they are really underrepresented in the pre-training data. So when it comes to, let's say, Nepali or African languages or Indic languages, you'll see that the data coverage is 0.0001% or none at all. And also, we don't have instructions for those languages. So how to kind of unleash the power of LLMs in those, let's say, underrepresented languages where we don't have potentially any data or any supervised data. So this work that hopefully will be presented at ACL. We just got the reviews, which seems to be good. So it's based on the underlying theoretical assumption is that it's basically the Bayesian inference assumption that if you get more in context examples, your task posterior becomes like a delta. So if you give more in context examples, or in context learning is basically finding the task in your pre-training data. Okay. So in context exemplars help LLMs to infer a pre-trained task. So in this case, the task here is how to translate from English to Nepali or Igbo. Okay, so that is, let's say, our task, and how we can invoke this task by giving in context exemplars. So that is what this paper is about. And our assumption is that LLMs can understand a language easily. That means it can express that language in English easily. But when it comes to generate a language in low resource languages, it has the difficulties. So that means translation from any language, any low resource language, potentially low resource language to English, probably easier because LLMs can express anything in English. That is our assumption. But when it comes to generating something in a target low resource language, there the LLM has difficulties. Okay, so that is, we'll show that. And yeah, as I said, like LLMs have perfect expressibility in English. So that means translating anything to English is easier, but translating from English to any other language is difficult, and especially low resource language is difficult. So let's see the first part. Expressing anything in a low resource language in English, or translating from a low resource language to English. And for that, we propose LDP, which is linguistically diverse prompting. So if you give exemplars from high resource languages like Russian, German, French, Chinese, as long as you are covering the scripts, then the language model will be able to find it, or will be able to find the task and do the translation. Okay, so this is easy. And that is what I'm referring to the NLU, or natural language understanding standpoint, that LLM can understand and express even a low resource language given sufficient number of prompts or exemplars in terms of English. Okay, so this is easy. And here's an example for Igbo. So basically, you provide all the in-context exemplars in Russian to English, Chinese English, Vietnamese English, French English, and ask LLM to express Igbo in terms of English, and it can do that. The problem appears when you try to do the opposite. So that means even the same prompting, the LDP would not work if you ask the LLM to translate from English to Igbo. So it just cannot identify the language tag. And the reason is that it has uncertainty on the posterior, on the target side posterior. So that means it cannot identify which language it should translate, because for the LLM, it's confusing. So it requires more examples in the target language to be more certain about the target language. Okay. So the solution to this is to have more examples on the target language in an unsupervised way, because remember that we are targeting low resource languages. And it turns out that the first one can actually solve that problem. The fact that we can express anything in English can work as a back translation to create synthetic English side data. Right? So that is what works. So this is the approach that we took, is that so we can create a prompting technique, which is LDP, for anything to English, just like what you showed. Now for the other one, we can use that prompting technique to create synthetic English data or back translated data and use that as prompt for the target language. So the difference here is that we'll be generating more synthetic data for one particular target language, which in this case is Igbo, and give many examples, and then the model can do that more accurately than it only sees maybe one example. Okay. And we can even extend this idea to do any language to any language by doing English pivot. Okay. So essentially, you can use either this one and this one to generate the triple data or the pivoting data through English, or you can just use this model. Just flip this pairs. This also works when you are doing from any language to any other language. Okay. And what you can do also is that now that we have a method to generate synthetic English, you can use that data to fine tune your model and get extra, let's say, synthetic data to fine tune. So that is what we call unsupervised fine tune. Yeah.
What you're first translating that before how do you know that the generated actually?
Oh, so this is you take so let's say you have monolingual data. In this case, let's say you assume that you have huge amount of at least few Igbo sentences. Now you want to generate the corresponding synthetic English. So for that you use this approach to create synthetic English and use that to prompt. So you take monolingual data, create synthetic English using the first one, and then you give more examples for that particular language, in this case Igbo, so that you can now then translate to Igbo.
Your book gets generated out of that with the water for it.
Yeah. Yeah, because you are giving more Igbo examples. So these are all Igbo. So the trick there was to actually get more Igbo examples with synthetic English.
Okay. Have you thought about using a metric other than live loss for training?
No, so just, I mean, we could not actually, I mean, we only did fine tuning with LoRa kind of approach, but here we could not do that kind of larger scale fine tuning. So we had to stick to the traditional one. So I think the main purpose of this work was not to actually do modeling rather than prompting, I would say. Kind of unleashing this capability from an multilingual LLM. So now it turns out that the same approach, or at least a slight variation of that, can be applied to many different tasks, like cross-lingual summarization, question answering, and even instruction following. So what you do here is that you use LDP prompting, like in, let's say you have a summarization task for which you need to do it maybe a language like Igbo, for which you don't have data. So what you do is you provide examples for other languages like French, Vietnamese, and Chinese, and use the same method to get the response. Let's say for summarization, the response is the summary, given the context. For question answering is the answer. For instruction following is the response. So you generate more examples for that particular task using this approach in your target language, and the same approach works. So basically, this is I would say, a very effective method when it comes to cross-lingual transfer using LLMs. Okay. So now let's see some of the results. So our main results will be based on Bloom, because that is something you know for certainty, for sure, what went to the pre-training data. But we also show results based on the Instruct GPT, Text DaVinci. And it turns out that I think the main finding here is that the unsupervised LDP, where we don't use any kind of label data or any translation data or supervised data, is as good as supervised prompting across 13 Indic and I think 21 African languages. And we proposed a kind of variation of LoRa where we only fine-tune the QKV weights rather than the entire LoRa. And it turns out to be also quite successful, that it could even achieve close to 170B model with a 7B model, with a, yes, 7B Bloom model. So then we show results for, let's say, high to high resource, then high to low resource, and also low to low. And it turns out that the unsupervised LDP is actually on par with supervised prompting in high resource languages, and also outperforms supervised prompting in pairs involving low resource languages. And also outperforms the existing method like XLT method from Huang. Any questions here so far? Then on summarization, yeah.
Here's, so this synthetic data for prompting makes a lot of sense. And when you have people try this for pre-training, right, you synthesize and translate millions of sentences of Igbo.
I did not see any method, but I think people have been, there is at least paraphrasing has been tried, like they, rather than translation, I think people tried models to do paraphrasing because they want to probably avoid the copyright issues. So I think there is one work from Hugging Face where they try to paraphrase the entire pre-training data or something. But yeah, I think that's a good idea to do. To get more synthetic, let's say, low resource translation data. Yeah. Okay, so now let's see results on the zero-shot multilingual summarization using the same approach. And again, like LTP, it turns out to be quite effective for this task. Summarization, again, for question answering on a squared and X squared and tight IQA with GPT, and also instruction following. So you can also check out the paper. So I think it should be at ACL. Okay, so any final question before I move to the third part of this talk, which is distillation?
So there's a way in which there's a way in which you can make an analogy between wanting systems to be competent multilingually and other kinds of invariants you might want to enforce that are often enforced by synthetic data or by playing with the objectives. So envision, maybe you're doing handwritten digit recognition, but you don't just take the original handwritten digits, you stretch them, you speckle them, you rotate them, whatever. So since you're building your own language model, I wonder whether you've thought about trying to change the objective to enforce invariance. So like it doesn't matter what language the input is in. That doesn't necessarily help you with the output part, but you might want to say that the distribution for conditioning on an input in English should be the same as the distribution when you condition on the Nepali translation, or at least maybe conditional up to translation, or conditional at maybe you control generation to force the output to have a particular language, then you're going to get pretty much the same strings.
Yeah, but I think it's probably very difficult to control at the pre-training stage because there actually you are dealing with, as I said, like at least 6 trillion tokens, and you don't want to 6 trillion tokens, and you don't want to mess up, especially when you are trying to compete and in a setup like, if Meta comes up with the next model before we do, then we are scooped. So we cannot afford. I mean, I think due to that reason, we did not do much of multilingual, I would say, applications of training so far at Salesforce.
Right, but you wouldn't have to do this on all the data. Like you would take some fraction of the data, you'd translate the prompt, and then you do the same kind of thing that you do in distillation, where the next token distribution, given the translation, should be similar in some divergence metric to the next token distribution, given between the two translations, versions of the prompt should be similar.
I think again, like unlike I think Meta at Salesforce, our team is not very focused to multilingual.
Yeah. Okay.
So we have Japanese as one of the main ones. So we care a lot about Japanese, but not like all the other multilingual languages. So that's why we don't have a dedicated team for multilingual, But yeah, I think probably Meta would do that. I don't know, but yeah. But it's a very nice comment though. That one nice question. Yeah.
The first claim that basically X to English is easy and English to X is hard. Did you actually run evaluations on translating into English? I'm just curious.
Yeah.
Okay, and how does it look for high versus low versus extremely low?
So you mean like high versus?
Across the region, is it that English, translating into English, basically is agnostic of the resource range of the source, or does it still degrade?
Yeah, I mean, obviously it will degrade based on the resourcefulness of that language, and you get better results on high resource languages. But I think the main fundamental problem is probably the opposite, rather than you get some meaningful translation at least when you're doing any language to English.
I mean, so in the sense that if that's true, then we have a great way to build lots of synthetic empty data sets, right? And which would then also be good going the other way.
Yeah.
So
that is what we did here, right?
Yeah. And another question that I had is, I'm wondering, so there's been some work recently in translating instruction tuning data sets into different languages. I'm wondering if you have a sense of how good those data sets would be in practice, would you use those instead of trying to do these other things?
So I think even the first author of this work, he actually worked on that. So I think the CLLM was actually trained by translating the instructional data, in particular the GSM 8K, into low resource languages. And I think he's very satisfied with the numbers.
Okay.
we're a bit short on time.
Oh.
To distill the final part.
Yeah. So I think how good how are you doing with the time? Okay. Okay. Yeah, I'll do that. So as I think, as you said, the data distillation, the traditional approach has been mostly like you try to distill from a closed API based LLM to a maybe open source smaller LLM, okay, which is the teacher. Now, the question here is when you are doing this, you are not taking care of the student. So you are kind of imposing what teachers think rather than what a student is capable of. So the question here is, can we personalize learning for a student model? And by personalize, I mean two things here. One is train on tasks that the student fails to solve. So that means personalizing on the input distribution or the prompt distribution. And then the second thing is, rather than imposing the solution, can we refine the solution or the initial attempt that the student made? So that is more of an refinement from the student perspective and also from the teacher's perspective. So that is output personalization. So now let's see the difference between the standard approach and the personalized distillation. So in the standard approach, the teacher generates the standard answer for a student to learn from. So there is no personalization. And we can use this to do code generation. And then on the personalized distillation, the teacher generates adaptive refinement based on the student's attempt and the execution feedback. So the student tries it first, runs it. If there is an error, then the teacher comes in, gets the student's initial attempt and the execution feedback, and tries to refine what the student has generated before. Okay, so that is the fundamental difference. Now, instead of doing this at the refinement level, you can also impose what the teacher has for the problems that the student faces. So teacher has his own solution, and the teacher will not take the initial attempt from the student, rather it will always impose the teacher's, let's say, the solution. So that is called input distillation, and you can do the same kind of fine tuning for that. Okay. So that is the whole thing, and that is, I think, everything all you need to understand this. So there's an example of that. So basically, in the personalized distillation, the teacher takes into account the student's initial generation and refines it. So now you have two kinds of supervision. One is the refinement solution, and also if you have a data set where the teacher already generated its own solution, you also have that solution. So yeah, I'll not go into the details of how you generate the data for this. So this was presented in last EMNLP, like in Singapore. And this is, I mean, again, this personalized distillation turns out to be quite effective. And you can do even multiple inference because you have now trained the model as a refinement approach, right? So you can first make an attempt. If you are having, let's say, if your execution is failing, you can make a second effect, and that time probably will be doing better. So we kind of show that in all these setups, this personalized distillation on code generation works really well. And you can essentially outperform a very large model with just 1/3 of the fine-tuning data. Yeah, I think that's all. And finally, I just want to just touch upon two limitations of the current LLMs. One is decomposition and planning that you all know. I guess the LLMs there, I think this is an innate shortcoming of the transformer architecture that this paper has been advocating for. And then the effective use of context. So even though we have many use cases where you need to use like RAG, retrieval augmented generation, but LLMs, they kind of fall short when it comes to effectively using the context. I think that's all from my side. Thanks.